Hello everybody, it's Professor King. This is a test video to see how the audio sounds and the video quality. This is about nuclear reactors. Right here you can see we're going to talk about Enrico Fermi in 1942. He constructed the first reactor under a squash court in the west stands of Stagg Field in the University of Chicago. The fuel elements contained fissile fuel. For example, it may be in the shape of the thin rods about 1 centimeter in diameter. In a large power reactor, there may be thousands of fuel elements placed close together, the entire region of the fuel elements being known as a reactor core. Here is a reactor. This is the core. This is the fuel elements, these rods. And these are the moderators that control and release how much the neutrons are being split. So back to what we're talking about. Uranium-235 is normally used as the fuel source, and it comes from uranium-238. The abundance of 235 is normally about 0.7%, but there are especially uranium plants that enrich it up to about 3%. Now, while neutrons with energies of about 4/100ths of electron volt or less readily fission to 235, the neutrons released during the fission process have significantly greater energies of several, like probably around 2 is the average, 2 MeV. Here, read this over here. This will give you a better idea. The neutrons released during the fission uranium-235 process, a continuous energy spectrum that spans from a few kilo electron volts up to over 10 mega electron volts, with an average kinetic energy of approximately 2.0 million electron volts per neutron. While the individual neutrons average 2 MeV, a single fission event releases an average of 2.43 or rounded to 2.5. Here, I'll show you what they're talking about. But anyway, the total is going to be about 5 MeV right here. I'll show you. So I take my rock off the page. Oh no, yeah, take this back here. Go to my notes here. Got this right out of the book. There's a 2.5 neutrons. You see the 2 neutrons right here. It's been split and they go off and they try to do the same thing all again. A chain reaction for clarity is assumed that each fission generates 2 neutrons, 2.5 neutrons. The one is lost. Right? I'll show you down here. There's a lost neutron right here. So, uranium fission reactor releases 2.5 neutrons. This makes it possible for a self-sustaining series of fission to occur, meaning going critical. So you have the 2 neutrons that are split, and it starts all over again to make a criticality. Then you lose it again. Right here's a loss, and it splits down here. That's a critical reactor right there. It's not subcritical, and it's not going supercritical, all right? There's also moderators. Usually the most common is water. The other one, they use control rods with, I think it's barium or something. We'll find out later. Just reading here, find out. If the output power from a reactor is to remain constant, only 1 neutron from each fission event must trigger a new fission, as in 32.5. I already showed you that figure in my notes. When each fission leads to 1 additional fission, no more or no less, the reactor is said to be critical. A reactor normally operates in a critical condition, for then it produces a steady output of energy. The reactor is subcritical when on the average the neutrons from each fission trigger less than 1 subsequent fission. In a subcritical reactor, the chain reaction is not self-sustaining and eventually dies out. When the neutrons from each fission trigger more than 1 additional fission, the reactor is supercritical. You don't want that. During a supercritical condition, the energy released by a reactor increases. If left unchecked, the increasing energy can lead to a partial or total meltdown, or China syndrome, so to speak, of the reactor core, with the possible release of the radioactive material into the environment. Yes, you don't want that.